All right, this is a little bit of a tricky problem, but nothing that we can't handle. We just got to be very careful when we go through this. So the question says that we have a block A with mass of 10 kilograms that rests on a 30-degree incline. I'm going to label that right now, and this has a mass of 10 kilograms. No friction, which is really nice, and it's attached to a string, runs parallel over the incline, and then passes over a massless, frictionless pulley at top. The B is dangling at the end. For which of the following will A remain at rest? So what is the mass of B? We want to know mass of B. What mass of B will cause A to not move? All right, so I'm looking at this picture. I see I have two masses. I'm going to do two free body diagrams. Let's do the free body diagram. So free body diagram of A looks like this. It has an mg pointing down, a weight force pointing down. It has a normal force pointing out of the surface, and it has a tension force pulling up the ramp. And if I do the free body diagram for B, I will see that I get an upward tension force and a downward weight force. And I got to be careful to make sure that I label this A and that mass B. All right, so I have some pictures. Next thing that I want to do is I want to draw a coordinate system. So my coordinate system for here, I'm going to choose a tilted coordinate system with plus x up the ramp and plus y to be perpendicular to the ramp. For my coordinate system over here, I'm going to say positive y is to the right and positive x is down. And this just means that if I go in x, this guy is also moving in x. So if I go up the ramp in x, this one will fall in the same positive direction as x. Okay, so free body diagrams. Let's do B first. That's going to be an easy case. I'm going to look at my net force is going to give rise to my acceleration. In the x direction, I get mg pulling down, a tension force pulling up, and mb times my acceleration a. Well, when I look at this case, it just says that the acceleration, or if I actually think back to my picture and what the problem is asking me, it says that this thing's not moving. So in this case, my acceleration is going to go to 0. So this gives me mg is equal to the tension in the string. And this is mg of B. Keep forgetting to draw that. It's in red, so I am labeling it, but I should be a little bit more clear. When I'm going through the problem for the free body diagram for block A, I'm going to use the free body diagram to give me Newton's second law. It says that my net acceleration is going to give rise to my net force is going to give rise to an acceleration. So in the x direction, I'm going to see I get a positive tension force up the ramp, matches my coordinate, and I'm going to get a negative weight force down the ramp. But I need the component of the weight force down the ramp. And I know that the 30-degree angle that they give me is this angle right here. I can actually look weight force down, and I can see that this angle and that angle are the same angle. So this is 30 degrees here. So that means to get the x component of this, it's going to be sine of our angle. And our angle is 30 degrees. And this is going to give rise to ma times its acceleration a. And again, we know this guy is not moving. So this just says that I get the tension is equal to mag sine of theta. And I know what t is, so I can plug in t. And t is mb times g is equal to ma times g times the sine of theta. And a factor of g will cancel out both, and my mass of B is equal to mass of A times the sine of 30 degrees. And the sine of 30 degrees is 1/2, so this is MA over 2. So I just have to figure out if I have a 10 kilogram mass as mass of A, then the sine of mass of A, 10 kilograms times the sine of the angle, is going to be 5 kilograms. So not that hard of a problem. We just had to be careful with our free body diagrams, making sure we get them all labeled the right way, and making sure that our coordinate systems, that we stick with our coordinate systems the right way. I had 2 different coordinate systems, but I found that I was able to keep them apart and solve the problem.